All right. Hi. I'm not really sure how to do this. I haven't done this very often. I am going to talk about my little project that I've been working on called ArchEvo. Now, I need to apologize. I'm not a video person, so my audio is probably going to be pretty bad. And I've also prepared a PowerPoint because, hey, I don't know how to do video editing. But at the very least, I won't do that thing where I only show the finished project at the end of the video. I'll show you it at the beginning of the video. Pictured here is ArchEvo in all of its glory. Here's the world window, all the cells duking it out. The characters on the screen are the different species, which share similar genetic properties. And you can also click on a cell to see what it's doing, what it's thinking, what its genome is, and you can see the dominant species down here. Now, if none of that made any sense, perfect. That will whet your appetite, hopefully, for my PowerPoint that I'm going to show you, because science shows that nobody likes PowerPoints unless they're actually interested in what's being said. So, crap. Wrong screen. Boop. There we go. Hopefully that'll, yep, okay. Hopefully you see that full screen. Anyways, this is called ArchEvo. ArchEvo comes from my GitHub username, Architect Drone plus Evolution, which is, it's an evolution simulator. Yes, all right, so ArchEvo is a generalized evolution simulator. It has no artificial incentives, which can be compared with, you know, evolutionary algorithms, which you may have heard of before. It was inspired by Tierra, Carrie Kh's Evolvio, and another one that I forgot to put on there was Adam, I don't know how to pronounce his last name, Yerymkio or something to that extent, Nanopond, which is very cool. So, all right, so let's talk about the system. It is composed, so the primary units of evolution are cells. All of them have 16 registers, 8 of which are physical, 8 of which are virtual, which I'll explain in the next slide. I think, yep, in the next slide. And they also have a genome of 32 instructions that are executed sequentially. So it's like a computer program, except that once it reaches the end of the computer program, it loops right back around to the start of the computer program, which I think is a little bit closer to how genes work in the real world, but that's up for debate. I just like it better that way because it's easier to understand what's going on. All right, registers. So we've got physical registers and we've got virtual registers. Physical registers are energy, which I'll discuss more in detail later. Guess and logo, which have to involve the combat system. 4 general purpose registers, which are just general purposes, and IPLOC, which is explained down here. IPLOC stands for investigation pointer location. And basically it just points at an adjacent cell to the current register. And the virtual registers are just the registers in that adjacent cell. So the ISA, or instruction set architecture, for those of you who might not know that, is what you might call an evolvable ISA, an evolvable instruction set architecture, which was inspired by Adam, once again, I can't pronounce his last name, Yerymkio, I'll just call him that, from Gray Thumb, I'll credit Gray Thumb, a talk that he gave. So basically the idea here is ISAs, for example, in your computer are generally very brittle. So if you flip a bit, the entire program breaks irreparably, right? The purpose of evolvable ISAs are to not break as easily and to preserve most of the functionality when there's small changes enacted to the code. So The ISA itself is a little confusing, and I made it that way because I hate you. Just kidding. Because um, it's because I wanted it to take as few bits as possible, and it ends up only taking up 11 bits. There are ROPs and COPs, register operations and cell operations. And operations are interpreted as cell operations if and only if it attempts to modify a cell that it doesn't have write operations for, or write permissions for. So those include its own energy, which obviously it'd be kind of a bust if you could alter your own energy. That would remove all evolutionary pressure. And cells in IPLOC, which are, owned by someone else. So here are the ROPs and the COPs. ROPs change the state of the cell. A is the first argument. And these are pretty standard. You've got increment A, decrement A, shift left logical, which if you don't know, just takes our 8-bit value that's an A, moves all the bits to the left and places a 0 at the end. Shift right logical is the exact same, except it puts a 0 at the beginning. SLT, SET, and SGT are kind of like Booleans. They do a comparison and they write a Boolean value to A. In this case, 0FF is Boolean true. Then we have, for COPs, we have div, which is reproduce, which I'll talk more about later. Jump, which uses Tierra's template system, which I talk about that in the next slide, so hang on to your pants. Jump compare, which only jumps if it's Boolean true, if register B is Boolean true. Nop A and Nop B, which are both part of the template system as well, and attack, which is part of the combat system, which will also be discussed later. So let me give a brief overview of the template system, which is not super hard, but a little strange if you've never seen it before. So when jump is called, these two, hopefully you can see my mouse pointer because that would be embarrassing. Let's see, do I have, turn on the laser pointer. Ooh, nice. All right, so after the jump pointer is what's called a template, and it is created by NOPs, Nop A and Nop B. And so when we get to a template, it'll look for the closest match to this template. I'm sorry, when it gets to a jump, it'll look for the closest match to this template. And it won't jump here to the next Nop because there's an even better jump location, which is here, because that's Nop A, Nop B, and this is Nop A, Nop B. So just thought I'd explain that, just in case you've never heard of that before. I hadn't. Certainly not a well-known idea. Now let's see if I can actually move to the next slide. Dang it. All right, reproduction. Cells can only reproduce when they have an energy above the initial energy. So all cells start off with the same amount of energy, and that energy is donated from their parents when they reproduce. Therefore, you can't reproduce if you have less than that energy. And therefore, all cells begin with the same amount of energy. Sorry, I'm kind of being a little bit redundant. This is one take, by the way. Don't get on me. And also, just like in evolution, some copying errors will be made. So that's how evolution works. That's pretty cool. Combat, all right. This is the last part of the system. So in order to get energy, because we need energy to reproduce, right? And that's the only evolutionary pressure in this system. They need to eat other cells. Now, so when the ATK command, which is a COP, is called, you gain energy proportional to the number of bits that are correct in the, so, okay, sorry, let me explain that a little better. In fact, I think I explained it even better over here. So let's say, so when attack is called, it takes your guess and it compares it to the victim's logo. And the amount of energy that you gain is not equal to the number of bits that are correct between logo and guess, but rather proportional to it. So if you guess 100 of the bits correctly, sorry, 8 of the bits correctly, you get 100% of their energy. If you guess 4 of the bits correctly, you get 50% of their energy. So yes. So in short, all you really need to know is that cells should try to make their logo as unpredictable as possible, right? To make it as hard as possible to steal 100% of their energy, which will kill them. And in order to reproduce, of course, and gain energy, they need to make their guesses as close to the other cell's logos as possible. So yeah. All right, now the program. So this is what the program looks like. You already saw it. I already did a brief explanation of the different parts. We've got species, and so we've got information about the cell here. Here you can see our 8 physical registers here, and our 8 virtual registers here. This is the world window. Species, which are just groups of cells that have a very similar genome, are displayed with the same character. And their color is common to all descendants of the same species. Sorry, of the same ancestor. And this is the scoreboard. Now, one thing I forgot to mention are tildes. Every iteration, some set number of random cells will be added. They are just filled with completely random bits in their genome. And they're the primary food source. And they're also what ends up evolving into these creatures if they're successful and end up avoiding the fate of being eaten alive. So yeah. So once again, I call these tildes. They're just the random bits. But yeah. All right, and also another function of the program is it generates these very nice log files, which tell you a little bit more in depth about each of the species, including its genome, prey, predators, average age, virility, which is the number of children it has, and name, which is really long because each time that there's a mutation, each time a new species spawns from another species, it takes its parent species name and adds a random letter to it. So yeah. But yeah, all right, results, the fun part. All right, so evolutionary, wait, before I do results, before I spoil that, actually I'll show you it in action after I finish the PowerPoint. All right, so let's talk about overall evolutionary trends. So generally we start off with a high degree of biodiversity between different species, and we tend to converge towards one phylum, which is just my way of saying all of the species that end up emerging tend to be from the same common ancestor. But an interesting thing is that even though there's no new phylums that end up emerging, there's really no end to mutations that I've ever seen. So there's always new mutations. I've gone as far as 4 million iterations out, which takes over 2 hours, and I've never seen an end to mutations. So there's a lot of cannibalism amongst species. They tend to eat each other. And originally I was expecting a lot less cannibalism because, and it's not just because it's a social taboo, it's because in the real world genetics, animals try to avoid eating each other on a genetic basis, because if they were to eat each other, they might be eating someone they're related to, which would be hindering the development of their genes. But I suppose that the benefits of fast attacking, like having a quick trigger finger on the attack, outweighs the costs of potentially eating a friend. So that's a little disturbing if you want to think of it as disturbing. There's one very simple strategy that almost always occurs in species. Is one of the very first commands that it does is decrease logo by 1, which, so all cells start off with the logo 0, 0, 0, 0, 0, 0, 0, 0, and we just change that over to 0xFF. Which, so if the guess is 0, 0, 0, 0, 0, 0, 0, 0, 0, which all cells start off with, and the attacker attacks you with that guess, you take 0 damage. So that's pretty nice. And that's one of the first things almost all species do. And it renders them almost immune to attacks from tildes, since tildes don't know to do that yet. All right, this is something interesting. The silver bullet genome. So, all right, so all the way back on my slide about the ISA, let me go back there. Wait, there it is, I went past it. There's a command which is move, right? Which basically just says, all right, I want to set this register to equal whatever this register equals, right? So if you're particularly keen and you were paying close attention while I was explaining the combat system, you may have asked yourself, oh, and why the heck would it not simply just copy from the logo, from the victim's logo, to the attacker's guess? Wouldn't that be perfect? The answer is maybe. Maybe. That was a speculation I had even before I got as far as to actually see what was going on with the ArchEvo Viewer. All it would do is just copy from the logo to the guess. But then I thought, hey, no, that wouldn't happen, because that would lead to killing or eating all of your children, which eating all of your children, which sounds really bad, is tantamount to not having any children, which is tantamount to not reproducing and being a failure of a species. Because there really wouldn't be any way to avoid that, or so I thought, without having complex jump commands using the jump conditional, which would allow any prey to quickly get out of range. So, did it arrive? Ooh, let's see. Yep, it did arrive. In fact, it arrived very quickly, sometimes within only 300,000 iterations. And the dominant life form tends to have this silver bullet genome. And it turns out that there's more ways to avoid eating your children than just using complex jump statements. And I hope I never have to say that sentence again. So as an example, the highlighted cell here is the very first cell that I spawn in this empty simulation. And you can see all of its children over here. And by the time that we actually get to the silver bullet genome, which is right here, all of its children are well out of the way. In fact, the only time that it actually ends up using the silver bullet genome against one of its own children is when it loops all the way back around to this side. So if the world were infinite, it could keep doing this forever, which is interesting. All right, conclusions. I need to end this project, all right? I've been working on this project nonstop for over a week, all right? That's just the way I am. I obsess over things. Fueled by nothing but pure autism. And I know that if I don't make this PowerPoint and video, I'm going to continue working on it for the rest of my life, and I need to stop it because it's getting frustrating. I need to work on something else for a change. So I'm going to make this open source, and hopefully someone else can pick up the torch. All right, so there are a couple problems. The world is very prone to data races because everything is updated top down, left, right. So cells over here will have a higher priority than cells over here. That's not good. We want them to happen simultaneously. Also, for some reason, cells very rarely evolve to use jump statements. I'm not sure if that's my fault or just the fact that jump statements are too costly to be used. And I have no idea if this ISA is actually Turing complete. So yeah. Normally I'd end with an inspiring message, but who cares? Screw inspiring messages. It's time for me to show you some of the functionality of the program. All right. Let me make sure. Hopefully, we can just switch over. The ArchEvo Viewer. Very nice. All right. So yeah, this is the ArchEvo Viewer. Here it is in real time. All of the flashes, so the red flashes represent a cell being eaten, and the green flashes represent a cell reproducing. So we are very early into this simulation, just almost 2,000 iterations. So let's speed it up a little bit. There's a fast forward mode, which skips rendering. So as you can see down on the species scoreboard down here, there's a lot of fluctuations. Let's take a look at the race of G's. This race of M's, I think, will eventually take over. So again, here is the cell's brain, one might say. Here's its energy, logo, guess, registers. Here's its genome. So right now, this next command is set if equal iplock to some I command. It goes off the screen. So that ends up setting iplock to 0. And basically, iplock uses one hot encoding. So you can always tell what iplock translates into with this symbol down here. So yeah, that's pretty much it. Let's see, what else should I show you? Well, I'll show you what a Genebank looks like. Here. So for this experiment, I went out 4 million generations, and I generated a Genebank. So there are, let's see how many species are in here. There are a whole bunch of species that have been recorded throughout time and space. Hurry up, please. I don't really know of any better way to count files. Oh, yes, I do. No, I don't. Oh, yes, I do. It's just right here, isn't it? Dumb me. So there are 501 species located in here. Is quite a bit. So let's go to one near the very end. All right. This is an extinct species. You can tell because it says extinct. It was very successful. It had 4,000 at its peak. Let me make sure you can see this. Dang it. Sorry, give me just a second. Actually, I'll just switch over to this one. How about that? Sorry, this is one take. So here's the genome. Here are prey and predators. So once again, there's a high amount of cannibalism here. It tends to eat itself more than any other species. Oops, sorry. I'm sorry. I keep screwing this up. I'm probably gonna have to cut most of this out. So we've got species name, which is very long. We've got genome, very cool. Average virility, just over 1, so that's pretty good. So that means it has at least 1 child, generally speaking. And we can make some observations if I, wanted to steal more of your time about what this genome is actually doing. You could see that most of the time, a move command is the very first thing that a cell does to get out of range before its parent attacks. In fact, this one moves 7 times before the parent's attacks. So that's pretty good. So you know what? I think I'll just end this video right here and check out the GitHub, run it on your own, and yeah, evolve on, I guess.